Here we're going to look at the solubility of group 2 compounds. We're going to look at two types of group 2 compound, the first being group 2 hydroxides. Now, group 2 hydroxides all have the general formula MOH2, where M is any group 2 metal, and solubility increases down group 2. Now that is something that you never need to explain. You don't ever need to know why that is the case. You just need to know that it does. This provides us a basis for the test for soluble magnesium and calcium ions. Now, what that means is if we've got soluble magnesium or calcium ions, so for example, magnesium chloride, we add a test reagent, and that test reagent is sodium hydroxide. What happens is once the magnesium ions in solution come in contact with the hydroxide ions in solution, they will join together to form the insoluble magnesium hydroxide. And the key now is we've got there a solid. Okay, so that would happen with magnesium or calcium because of the lack of solubility of the magnesium or calcium ions, and that's why we put there a solid. And to balance this, we'd need two NaCls. Now, again, this is less likely to work if you've got strontium or barium, because they're more soluble. You wouldn't get any observations. So we would observe this here as a white precipitate. And if we add an excess of this sodium hydroxide, the white precipitate remains. And that's my positive test for magnesium or calcium ions. We add sodium hydroxide, we get this white precipitate of magnesium hydroxide. And when we're in an excess of this sodium hydroxide, the white precipitate remains. Now, this is usually simplified to an ionic equation because we've got chloride ions in solution, sodium ions in solution as my reactants, and I've still got sodium and chloride ions in solution as my products. They in effect can cancel out, so we basically get rid of these, and that then can be written as an ionic equation. And this is what's more likely to be asked, where we've got magnesium ions plus hydroxide ions, and that gives us my magnesium hydroxide. And that there is the ionic equation for the reaction of any soluble magnesium salt and sodium hydroxide. Now, the solubility of these group 2 metal hydroxides increase as we go down group 2. So we've got magnesium hydroxide, calcium hydroxide, strontium hydroxide, and barium hydroxide. Now, because the solubility increases down group 2, this will affect the pH of the solutions. Now, when you've got a solid metal hydroxide and you add water, what happens is then an equilibrium is set up and we form the aqueous ions. The more soluble the group 2 metal hydroxide is, the more the equilibrium lies to the right and the more hydroxides ions we have in solution. So hopefully you can see, because the solubility increases down group 2, the equilibrium is going to lie furthest to the right with barium hydroxide and furthest to the left, if you like, with magnesium hydroxide. So what that means is that as you go down group 2, the concentration of these hydroxide ions in solution will increase. So as you go down group 2, concentration of hydroxide ions increases as you go down group 2. And because of that, that means that the pH of the solutions increases as you go down group 2. The higher the hydroxide ion concentration in solution, the higher the pH of the solution. And that's something that you would learn about in acids and bases. So that's group 2 hydroxides. We're going to take a look at now the next group 2 compound, which is group 2 sulfates. And they've all got the general formula of MSO4. And we said there that the solubility increases down group 2. Well, it's the opposite for sulfates. Solubility of group 2 sulfates decreases down group 2. Now, that brings us on to what some people may find as a useful mnemonic, and that is ham salad. Now, what does that mean? Well, it means that hydroxides are more, we're talking about solubility, sulfates are less, again, soluble, as you go down group 2. So that's a mnemonic that you may find useful. We're talking about solubility. Hydroxides are more, sulfates are less as you go down group 2. Now, the solubility decreasing down group 2 gives us the basis for a chemical test for soluble sulfate ions. Now, what we would do then is you'd react these soluble sulfate ions with a soluble barium salt, such as barium chloride or barium nitrate. And that then would react with a soluble sulfate, such as sodium sulfate. Now, what happens here is once the barium ions in solution come in contact with the sulfate ions in solution, because the solubility decreases of these sulfates as you go down group 2, barium is at the very bottom of group 2, and barium sulfate is very insoluble. Therefore, you'd observe a white precipitate of barium sulfate, and therefore we express that as a solid. And we also get 2 NaCl's. So again, this gives us the basis of the test for soluble sulfate ions. We've got my soluble sulfate, and my test reagent is any soluble barium compound. And because when the barium meets the sulfate, we get a solid barium sulfate. A white precipitate is observed. Now, this is usually again written as an ionic equation because we've got chloride ions in solution here, sodium ions in solution there, and we've still got sodium and chloride ions in solution in my products. So again, in effect, these chloride and sodiums cancel. And that gives us then the ionic equation of and this is what you're more likely to be asked. And that there is my Ionic equation. So that is a quick look at the solubility of group 2 compounds.